about, all right, hard problems. Oh, the midterm grades are up. So let's see, I should have somewhere my, apparently not. There we are. Yeah, so they're up in Canvas, and I'll put them on the City College system this weekend. So if anybody needs to know that, you can look it up on your Canvas scoreboard. And so today we're down to hard problems, which is a bit of real computer science. A relatively new thing for me. I haven't really studied much computer science, but this is about as close as I get to it, computer science and set theory. So this is how hard things are. And the important thing for us, which is perhaps disconcerting, is cryptography is based upon no firm mathematical foundation at all, really. People have tried for a long time to prove that certain operations would really be cryptographically strong. And in fact, it is not resting on anything resembling real proof. So there is this thing called computational hardness, which is the order of a problem. And this makes sense. So there are some problems that are extremely difficult to solve. And what you would like is you would like to have an encryption scheme where getting in without the key is provably extremely difficult. And but there is some way to get in with the key that is not difficult. So what you do is you figure out how quickly a problem changes its running time when you scale and make it bigger. So if you have n elements and you're just searching to try to find if something is in there or not, then you're hunting for something in there. If you have to look at every single one, that will take n operations. If you find it, you'll have a chance of finding it about halfway through on the average. So the expected amount of time it'll take to find an object is n over 2. That's linear. So if you double the length of the list, you double the running time, and that's considered an easy problem. In fact, any power law, like quadratic, is also considered easy. The things that are considered difficult are exponential, and so on. And there are things in the middle, like linear logarithmic. If like sorting a list, as you know, if you wanted to sort a lot of items, you could just sort by the first digit into 10 piles, and then sort each one of those piles by the second digit and by the third digit. And that's why it's n log n. You only have to sort smaller and smaller piles. So you have to do a log n series number of passes of approximately n each. So that's less than n squared. And so that's considered an easy problem. So in general, your linear problem is here, the quadratic problems are here, and exponential is much, much faster, like 2 to the n. That is considered difficult. And so polynomial time is anything like this, n squared, n cubed, n fourth. All those are considered easy. Super polynomial is something that grows much faster than that, like 2 to the n, or n to the n, or n to the log n, things like that. Those get big so fast that it is easy to make a problem that exceeds the capacity of any hardware you can afford. So that's the qualitative distinction between easy and hard problems. All right, so that you can talk about time complexity is what I was just talking about, how many computations and therefore how much time it'll take. So it would take n squared computer cycles or seconds or something, or 2 to the n. And then you can talk about the memory required. The memory can grow similarly. It might grow up linear, it might grow quadratic, or some other rate of growth. Either of those will do, of course, because you have money. There's a limit. Log n will, yes, log n will grow slowly. So n log n is faster than n, but slower than n squared. Yeah. So that's back here. Yeah, n log n is here. And n squared is this one, which this is n2 to log n. Oh, right. But n times log n is going to be less than n squared. Yeah. Anyway, so you can determine the difficulty of these, and this is the famous issue of P and NP. So P is the class of all polynomial time algorithms. Anything you can say you can solve with an algorithm quickly. And NP is the class of things that cannot be proven to be solved quickly. However, there are problems where when you find the answer, you can solve it quickly. And of course, the whole point of cryptography, and for that matter, puzzles and games, and the whole discipline of mathematics, where you study and work hard to solve problems, is based on the idea that NP is not equal to P. If this is the question, if you are a mathematician and you study hard to solve hard problems, have you accomplished anything, or are you just stupid? Is it that all problems are easy? If NP was equal to P, then all problems would be easy. It's just that you haven't found the fast algorithm yet. So when you don't have a fast algorithm, then you call that problem NP. If you can tell that you've found the answer once you find it, but it's difficult to find the answer. This is, of course, what we would call interesting problems or difficult problems. And you would like to think, anecdotally, as you take calculus and all these math classes and you learn to do more and more complicated operations, it seems like there's a whole bunch of hard problems and you need to develop these better and better techniques to solve them. But maybe it's all an illusion. This has never been proven, which is sort of disconcerting. So here's NP problems. It's recovering a secret key with known plaintext. So you're trying to find the key that turns cryptotext into plaintext, and you know the plaintext, but you don't know the key. And that is a hard problem for something like AES. But if you ever find the key, it's easy to verify. So that's an NP problem, where you can tell when you've got the answer, and that's easy, but there is no known way to do it fast. And that is something that would make a good cryptographic system if you were only sure that this was going to stay hard. All right, so, and they call this the nondeterministic problem. A deterministic problem is like sorting a linear list, where you go for a certain number of steps and then you're done. It will never take longer than n steps before you can say absolutely whether you found it on that list or not. But non-deterministic problems have a sort of randomness to them, like you're guessing numbers for the key. You can't say how long it'll take, and it might take forever, and you still haven't answered the question, or you do not know how long it's going to take. Those are the NP problems, where you cannot say when it's going to end. Now, there are some problems that are outside both of these groups. For example, if you brute force the one-time pad is that wonderful perfect encryption scheme where you have a different key for every character in the plaintext. And you modify you turn it into ciphertext with a separate key byte for every byte of plaintext. There's no pattern at all. And what that means is if you were to do a brute force attack and try every possible key, you would produce every possible result, including every possible plaintext. So you'd have no way to spot the right one. So they can't recognize the solution when you find it. This is a very hard problem. It's fundamentally impossible to solve by any known method. So it's not NP and it's not an NP. You can't even tell the answer when you find it. So another one that is simpler is the one that, of course, we're sort of dancing around. You would like to take a problem like AES or RSA encryption, and it would be nice to prove that there is no fast solution. And that proving that there is no solution is a hard problem. That's a really hard problem. That's harder than either of these. Nobody knows how to prove that you can't find a solution, and that is very disturbing. That means you really don't know that your secret transmissions are going to stay secret. You can't mathematically prove that your enemy doesn't know a mathematical trick to get in. That's where we are, though. So the hardest problems in that group of NP are the NP complete problems. We don't know how to solve them, but they're all equally hard. There's a whole series of problems that look different, but they're all mathematically identical. And if you can solve any one of these, you can solve them all. And these are the classic ones used for challenges in computer science problems and such, like the traveling salesman problem. You have a set of cities to go to, and you're just trying to find the shortest route that will visit every city, which might sound easy, but it turns out to be extremely difficult and to get much, much harder as the number of cities goes up. Another one is if you have a group of people, and each people have direct connections to some other people, but other people, they're only friend of a friend, you might say, what is the largest group of people where every one of them knows all the others directly? So these are the nodes that are connected directly by lines, but down this one is separated. So this is the clique, the largest clique in this graph. But as this graph gets bigger, that also becomes extremely difficult to determine. And as you can see, this is very closely related to the traveling salesman problem. We're just trying to find the shortest route that will visit every town. It's a very similar issue. And a third one is also mathematically the same. You have a set of items and you're trying to fill a knapsack, and you can only carry a certain amount of total weight, and the items have some value, and you're trying to figure out what mixture of items would have the most value and still fit within my weight limit. There was one of these I saw in a captured flag competition where they said you're trying to make a captured flag team, and you have each member in your team has a certain weight and they have a certain skill, and your car can only carry this much weight. So how do you make the most likely to win team? You have the strongest people with the total number of weight. And again, all these are extremely difficult problems. So those are NP complete problems. They're all mathematically identical, and there is no known solution for any of them. If anybody ever finds a solution for any of them that's fast, they will all get easy. And it turns out video games are typically this type: Tetris, Super Mario Brothers, Candy Crush Saga. Those video games are all NP complete. They're all mathematically identical to those other problems. Now, there are some even harder problems than the NP complete problems, and those are the NP hard problems, which might be outside the entire group of NP. So, all right, so if you could solve the hardest NP problem, then you could solve them all in polynomial time, and then all of them would be easy. Yeah, this is very much like those Google interview questions. Anyway, so there is a $1 million bounty out for proving this. This is whether if P equals NP, this would rock the foundations of mathematics and philosophy, and it's one of these in principle. In principle, it would mean that all mathematics is just stupid, and every problem is really easy, and all the fancy techniques are really not necessary. However, in practice, it might not mean so much, because it might be that you prove that in principle, there is a efficient solution for every problem, but in practice, that solution is very hard to find. So we're back to where we are right now, where we continue to do things like cryptography, posing our enemy a difficult problem with still some reasonable belief that that problem will remain difficult, even though it is not absolutely fundamentally impossible for there to be a smart solution. They won't find one. So that's this fundamental issue you hear about a lot. Does P equals NP? Intuitively, it seems obvious that it does not. There are easy problems and hard problems, and it does seem like there's a qualitative difference between them. But here's the situation. You have NP, all the problems with an indeterminate amount of time to solve them, and you have this inside there's a small group of the easy problems, the ones that you can really solve in a reasonable amount of time. And then there's the particularly hardest ones of those, these NP complete ones, like the knapsack problem. And then there's all the ones in between. This is the situation that we believe to be true. All right, so you might think then that the best thing to do would be to use these NP complete problems for your cryptography, because they are the hardest of both the NP problems. But it turns out that these are not very well designed for cryptography. And by the way, quantum computers use an entirely different set of algorithms, and so people are trying to figure out where they fit in this graph. And this is the current theory, that there's problems out here that are completely outside of NP that are then easy for quantum computers. So right now, quantum computers are in their infancy and they can't really do much. But like I say, they'll throw quite a monkey wrench in this when they actually work. And so here's an example from XKCD. You have a menu with a certain price for every item. And if you just tell the waiter that you want an exact amount of money, that's the knapsack problem. How many combinations are there of this that add up to exactly one total? That is, in principle, a very difficult problem. Although, of course, if you only have 6 or 7 choices like this, then you can do it by exhaustive search, by just trying all combinations. The point is not that small problems are impossible. The point is that it grows extremely rapidly more difficult as it gets bigger. All right, so if you used NP complete, it would seem like it's a very strong cipher, but the problem is these NP complete problems are sometimes easy when you might think they would be hard, and they're sometimes not unique in their solutions. So it turns out they're not really as good for cryptography in practice. All right, and Lattice, there is one that we have actually already used. If you did the extra credit stuff, that crazy homomorphic encryption stuff uses lattice encryption, the stuff that was incredibly slow. And that is also one of the leading contender for a quantum proof algorithm, learning with errors. And that's actually an NP hard problem. That's Google's proposal to defeat quantum computers is the new hope. It's a lattice problem, learning with errors, and it does work on an NP-hard problem. It's the only one known to be successfully used in cryptography. But nobody's using it yet. People are just trying to understand it, trying to get prototypes working, and trying to decide if it's really going to work. All right, but what we are using is the factoring problem, like RSA. So if you have a large number n and it's the product of two primes, can you find P and Q? For millennia, people have wondered about this and nobody's ever found a fast way to do it. So now you could start making algorithms to do it. The whole point of prime numbers is you can't divide them by anything smaller except 1. So if you want to find out if something is a prime number, you could just try dividing by every number from 2 up to one number less than n. And if all those do not divide evenly, then it's prime. So that's an answer, but it will take n steps, n divisions. So if your n is the number of bits, you have 2 to the n steps. So that's a hard problem. You had 256-bit number, it'll take 2 to the 256 divisions to decide if it's prime with that algorithm. So that's certainly a hard problem by that algorithm, but there are better algorithms. For example, you could try only the prime numbers. If it doesn't divide by 2, you don't need to try 4 and 6 and 8, so you can try less. That turns out to be saving you a lot of time. For 256 bits, you'd only have to do 2 to the 120 operations. And then the fastest known algorithm is this thing called the general number field sieve, which is pretty complicated, but it's really fast, as you can see. If you have 1024-bit n, you can crack it in 2 to the 70 operations and 2 to the 90 for 2048. So this is why the current recommendation is that we should be using 4096-bit keys for RSA, and that'll be about 128 bits of security, which is considered effectively uncrackable. Even by the fastest known algorithm. But we've already been through 3 generations of algorithms here, and they got much faster. We went from 2 to the 256 down to 2 to the 120 and something much faster here. So how do we know there isn't something much better that'll break this down further? And the answer is we don't know that. All right, here's the experimental results in the real world. 663-bit n was factored in 2005, a 768 in 2009. And so people suspect, now that it's 11 years after that, they suspect that the NSA can probably factor a 1024-bit prime because they have the smartest mathematicians and an enormous amount of money. And, you know, it looks like that's not out of reach. So that's why a 1024-bit key, people are pretty nervous about that. There is no public demonstration of anybody cracking a 1024-bit key, but it is considered probably that the most powerful attackers can do that. All right, so like I say, factoring is certainly an NP, but it's easier than NP complete. At least it would appear to be. There is no way to make this equal to the other NP complete problems that anybody else has ever found, so that means it must be one of those easier problems. But of course, none of this has been proven because we don't even know that NP is bigger than P. So you can't possibly prove that the relative difficulty of different problems in NP. Anyway, quantum computers can divide things. Here's, if you want to factor 7 times 13 mod 15, you do it like guitar strings. You have these quantum objects connected together by these weird quantum properties, and now you put in a number that's a product, and it settles down to the factors with all these things just interacting in a complicated way. You do not go through algorithms or steps. You just stimulate the system and this answer comes out. This is like a flute. You blow in white noise and the properties of the flute cause certain frequencies to be enhanced and others to cancel out, so you get a note out of it. That's the way analog computers are. You just design a circuit that will converge towards the right answer. And that's how quantum computers work. All right, so anyway, that's cryptography. This is where we are. You have a problem that appears to be hard, and you assume that it's hard, and then you try to prove that your encryption is at least as hard as that known hard problem. This is, when I was young and learned mathematics, I thought mathematics was wonderful. You prove things that are really true. And when I actually started learning about real research grade mathematics, they say, you know, nobody ever proves anything in mathematics. All you do is you make arguments that convince other mathematicians. And that is not at all as firm as you might imagine. And that's what's going on here. So factoring discrete logarithm are used as hardness problems. These are well-known problems that are considered to be hard. And so you want to convince someone to trust your cryptography system. You typically show that it is at least as hard as one of these known hard problems. All right, so the discrete logarithm problem, we've already talked about quite a bit as we went through Pollard's row, and it's based on a group. Now, a group is a general mathematical concept that is necessary for cryptography. So you have a set of elements and an operation. These are things like numbers and multiplication, for example, although they could be more abstract. So the main group we care about is Z star P. That is the numbers from 1 to 1 before prime number, not including 0. So Z star 5 is 1, 2, 3, and 4. This group turns out to have a lot of nice properties. So here's the things you want it to have. Closure, we've talked about before. If I put in a byte of plain text and I encrypt it, I would like to get 1 byte of ciphertext. I wouldn't like it to have a random unpredictable size. I want it to just go around these possibilities. So that's closure. And when you combine 2 elements, you get another element that's still in the same list. Then you have associativity, where you can rearrange the order of operations and it doesn't matter. And then you have an identity. There is an identity element, so that if you multiply it combine it with one of the other elements, it doesn't change it. This is the 1 times, for example. And there's an inverse. If you multiply by something, there is a y that will get you back where you started. And that means that x times y is the identity element. This is super important, of course, because if we're going to encrypt something by multiplying them with a key, we'll never be able to decrypt it unless there exists an inverse. So we definitely want this property. If you don't have this property, then there are values that destroy information, where you scramble, you modify things, and there is no way to come back. And that's not what you want for encryption. All right, here's some other things you might like. You might like the reverse operations to be the same as the forward operations. And you might like groups that can be generated. So you can have a generator, and then if you do this Pollard's row thing we did, where you just keep doing the operation over and over again, so G to the first, G to the second, G to the third, that will go around all the elements. All right. So those are groups with all those properties are the kind we like for most cryptographic problems. And now you can make the discrete logarithm problem. If you have all those properties and you know that you're trying to find a y, so you take your generator to this y and you get the value x. You know it exists because you decided to use a group where there is a generator taken to every possible power will generate every possible element, but it's hard to find. And this is, if in this case of multiplication, this is the logarithm. In the more general group theory sense, it's the discrete logarithm problem. And that's the game here. And it turns out this is what RSA uses. And all right. So that's the hard problem. And it is considered hard traditionally, and we're all trusting that it will stay hard without being able to really prove that. So there are things that can go wrong. One possibility is somebody would find a fast algorithm to factor numbers, even though thousands of years nobody has found it. If they found that, that would be a backdoor into RSA. If somebody proved that P equaled NP, that might matter and it might not matter. Now, if they proved that in some philosophical pure sense, P and NP are the same, but in practice, finding those hard proofs is very difficult, then we'd really be essentially where we are now, where we can still keep using our cryptography because if there's a fast solution, it's hard to find. But if they found an efficient way to find those fast solutions, then of course that would solve all these NP problems and all this type of cryptography would be shot. Anyway, sometimes some of these numbers are easy. This 1024-bit number is not the product of 2 primes, it's the product of a bunch of primes. And because some of them are small factors, you can find them pretty quickly and then make it faster. So, you know, there are numbers that can be factored quickly. If P and Q are not random, which we already talked about, this happened quite a few times. It happened with public keys on the internet and elsewhere, that the random number generators were not random enough, or if they're near integral powers of 2, or if you have some information about them, that makes it easy. And of course, if n is small. like 128-bit RSA, or for that matter, 1024-bit RSA, then this gets too easy to solve. OpenSSL, the library, lets you make short private keys. You can make keys as short as 31 bits, which is, of course, completely insecure. So you, in practice, it might be wiser not to allow you to use keys that are so short, but this library lets you do it. The original RSA paper came from 1978, and at that time, based on the computing power at the time, they figured out that you'd never be able to crack something that was 100 digits long, would take years, and they recommended using 512-bit RSA keys. But of course, computers got faster to where that is completely not safe now, and now we recommend 4,000-bit keys. And that's, of course, the fundamental problem, that every system you make a few decades down the road is now not considered safe. Let's see, if you solve the hardest NP problems in polynomial time, you could solve all NP problems. Yes, that's what it would mean. That would be the most extreme solution, a proof that NP equals P. If you found a way to solve NP problems in polynomial time, that would not only prove that P equals NP, it would prove that you can find those fast solutions. That would be the most extreme failure, disaster causing P equal to NP, and it would sort of rock the entire foundations of mathematics. But everyone thinks that that is never going to happen. At least that's the general belief. But we don't really know. All right, so then you got, there's other real world failures of Diffie-Hellman. The Logjam attack is a huge problem because the US government decided to limit the export of strong cryptography, which, by the way, the Five Eyes are now trying to do again. They poisoned the world with all these servers and cryptographic systems that are using weak cryptography. And even decades later, you can still trick those servers into using the weak cryptography instead of the strong cryptography, which is why the mathematicians always hate it when the spies and governments do this. It's like poisoning the water. There's now this bad stuff out there that is just going to linger in the environment for decades and and that's the problem. That's a logjam attack. You intercept signals in the middle and modify them so that one server at the end believes that you're using one of these old systems, and until no system still supports any of those old cryptographies, there are systems out there holding data that are not secure because they can be tricked into using the old insecure protocols. And there are some cryptographic systems where people just keep using the same prime numbers for everything. There is a belief in Diffie-Hellman key exchange that it was perfectly fine for everybody to just use the same prime number because you combine it with another number. And it turns out that if you do know one of the prime numbers that's used to construct the key, that does in fact make the solution much faster. So there is a belief which people have deduced by watching what the publication of what has leaked out of the NSA suggests that they do in fact have solutions for those commonly used prime numbers. And therefore, a whole bunch of people are encrypting stuff with and creating the NSA's goal, which is what they call no-bus. They can encrypt stuff and nobody can get in except the NSA. That's what the NSA really wants. They want to have a secret backdoor that nobody else can find so they can read stuff, but it's safe otherwise from criminals and other enemy agents and such. That's what they would like. And that is a very difficult problem. And that's why the serious cryptographers are always very mad at the government. They say, don't try to solve that problem, where you make cryptography that has one backdoor and you can somehow keep that backdoor secret. They say that problem is too hard. You should just have strong cryptography that nobody should get in, and you should have to accept as spies that you can't get in without finding some other way in, like just putting a camera in your house or something. And that battle goes back and forth. So anyway, here's the results of that paper. This is the downgrade attack, and you see a lot of machines out there, like maybe 10% of them are still vulnerable to these old cryptography. And if this 1024-bit group is broken, then an enormous number of machines are using these known prime numbers, which would then be crackable. So this is the current state of things. Anyway, I've got some Kahoots about that. Here they are. This is chapter 9 or 10. Let's see, it looks like chapter 9. So this one right here. Okay. Oh, it must be Halloween. All right. Give it 10 more seconds. All right. All right, what's the hardest problem here? Right, exponential, typically 2 to the n. All right. Which one of these is the easiest? P, the ones that can be solved in polynomial time, are the easy ones. All right. Which one of these is the knapsack problem? Okay, that's the NP complete problems. All right. How about factoring? NP, not as hard as the NP complete or as hard as the NP hard. And that might be a reason to be nervous about it, but that's where we are. That's what the factoring problem is. Not known to be easy, but not known to be all that hard either. All right, how long should an RSA key be? Okay, that's it. 4096 bits is a good size these days. All right. All right, you'll have to tell me who they are if they want their points. Howard, I agree with the sentiment. Don't forget to vote. Okay, good. I see your name, vote. It's a good name. Let me put it up here. All right. So I'm going to stop the recording and post it. I'll stick around to answer questions.